All right, thanks for the introduction. So my name is Todd Kaplan. I'm going to be talking about a chip that we made called the LTC 2983 with Analog Devices. And it was with 3 designers, so I was the analog lead for it. My boss, Mike Mays, is a chip lead. David Bliss did the digital for it. And this chip kind of had a different set of goals than what you normally think about with temperature sensors. Of course, we want, a very accurate temperature sensor. We want it to have low noise, low power, optimized according to all these, different parameters that we've seen before in these talks. But on this, we're trying to optimize for something different. We're trying to optimize for ease of use. Because even with a lot of high performance components, it's still very easy to get burned when you're trying to measure temperature. So in industry, there's a lot of people, industrial users, these grizzled veterans who know where all the bodies are buried when they're measuring temperature. My understanding after this morning is about 75% of them now work at ASML. So there's not enough left over for everybody else. And the typical customer for this chip is somebody who really does need a fairly accurate temperature, but they don't know how to do it correctly. Okay. So specifically, what we wanted to do was have a multi-channel part. We wanted to do 20 channels, and we wanted to be able to do any sensor and any input. It didn't really matter. We can program it, we just program the chip to accept anything. It can handle thermocouples, RTDs, thermistors, diodes. It could also handle custom sensors, but we won't talk about this in this talk. And this is, now we're, okay, I'm going to avoid the mouse. Okay, the other thing we want to do is we want to make it very easy on the user. Okay, so they only need to put bypass cops on each channel. They don't need to put anything fancy on it. They can be ground referenced. You don't need to do any external biasing. And the other thing is, if you look here, they can use over 10K protection resistors. Okay, so when you think about an industrial setting, you're going to have somebody with, for example, with a thermocouple, some worker kind of like exploring around and oops, they just shorted it to a 120 volt supply. Okay, so they wanted to make sure that the chip isn't going to fry when that happens, and because of that, they want to put in maybe 10K, maybe even more, depending on what their supplies are. And we wanted to make it easy on the user by having only a positive supply and ground, no negative supplies. So what we're going to find out is by trying to make things very easy on the customer, we're going to make things very hard on us. Okay. So I guess any decent self-respecting circuits talk is going to have something about architecture, so it's over here. So if you go from left to right, basically to handle every channel and every sensor, of course, we're going to need a very big mux, so we have that, and we tend to have it isolated with its own wells. From there, the signal gets buffered, and you'll see why we're going to have to do that in a little bit. Okay, and from the buffers, then they go into an ADC, and the ADC is a third order delta sigma modulator with a sync 4 filter at the end of it. And the advantage of doing a delta sigma modulator is they tend to reject a lot of high frequency noise. Because it's such an oversampled system, you have to go to a much higher frequency before it aliases back to DC. And furthermore, if you set the sampling frequency right on the delta sigma and you have enough samples, you can also notch out 50 or 60 hertz noise. And in an industrial setting, that's a pretty big deal. That can dominate the inaccuracy of the measurement. And we're going to see that we're going to be able to exploit the delta sigmas notching out of higher frequencies a lot in the future talks. Okay, now at the bottom there's some excitation current sources. We're going to need those to measure diodes, RTDs, thermistors. And on the right we have a processor, and so the way a processor works is you have a voltage. We have to turn the voltage into a temperature. We have to turn it into a temperature for all kinds of different sensors. They all have their own math behind it, so that's what that does. So as you would probably imagine, I'm from ADI. A lot of this is proprietary, so most of the stuff that's pretty interesting I can't talk about. But what I can say is even with the fanciest components here, you can still measure temperatures pretty inaccurately. Okay, so how does this all work? Okay, so let's go to the first sensor that we're going to use as a thermocouple. So I'm not going to try to go too much into detail about how thermocouples work because this is something you can Google, but I wanted to give enough of an introduction into thermocouples so you can understand the design challenges of it. Okay, so if you look in the on the top left, this is the basic idea of a thermocouple. And if you have a piece of metal and the ends are at two different temperatures, then you can actually generate a voltage. Okay, and then that's known as the Seebeck effect. Okay. So the way you exploit that is you have two different metals. So you have a purple metal here. That could be like, for example, chromel, some very funky alloy. Alumil could be at the bottom, and they have different Seebeck effects. So even though it's the same delta T, you're going to get a different voltage across them. And so if you measure the voltage at what's called the cold junction, where the chip is, and you know the temperature of the cold junction, you can deduce what the temperature of the thermocouple is. Okay, so that's the basic idea of how a thermocouple works. So on the right, you can see this graph of the EMF that a thermocouple produces as a function of the temperature if the cold junction is a bucket of ice water. Okay, so you can see that it's roughly depending on the sensitivity somewhere between 10 to 40 microvolts per degree C. So you do need a pretty sensitive detector to be able to handle that. But the other thing to notice is for high temperatures, it's positive. The millivolts are positive, but there's nothing to stop the thermocouple from going to a lower temperature than the cold junction. And if that's happening, you're generating a negative voltage. Okay, so let's put that in our back pocket for a second. Okay, so let's look at a practical thermocouple sensor. Okay, as I mentioned, you're going to need to have protection resistors on this because you don't want to, you don't want to fry the chip when you short it. Because you have these protection resistors, all of a sudden, it's not going to be, it's going to be much harder to just feed it into a capacitor on an A to D converter. Okay, you can have all kinds of problems with, with the resistor divider. So it's a lot better if you buffer it. Okay, so now you have to buffer these signals. Okay, fine. Now, these thermocouple voltages may go low, so it would be nice to have a negative supply, but we don't want to do that for the customer. We want to make it easier on them. All right? Oh, geez. So, yeah. The reason I'm laughing is I actually got instructions to restart this computer about an hour ago and did it at great risk to this talk, and now it's acting up again. So my next computer is going to be a MacBook. Anyway, so back to the main event. We're only allowed to use a positive supply and ground. Okay, so you have this voltage. You have a buffer. Buffers can't really handle ground inputs very well. So maybe what we should do is we should just bias up the thermocouple so the buffers can handle it. Well, we don't want to do that either. That's hard on the customer. We want the customer to be able to just ground one end of the thermocouple. Okay, so here we are. We have the situation where the customer might be able to ground one end of the thermocouple, generate, say, minus 50 millivolts, minus 100 millivolts, going into a buffer, and then we have to be able to process that accurately without a negative supply. Okay, so how do we do that? Well, step one is let's just generate a negative supply to begin with and worry about how we do this, how we're going to handle this later. So we're going to use a charge pump. Okay, and this is a pretty vanilla charge pump actually. So if you look on the top, S1 and S3, it goes in two stages. In the first stage, S1 and S3 are on. You charge up the top of C1 to a voltage, which is approximately 200 millivolts in our chip. When you do that, S1 and S3 close, S2 and S4 open, S1 and S3 turn off, S2 and S4 turn on. It connects to the top, connects to ground that drives the voltage at Q2 to minus 200 millivolts, and we have our VSS. Okay, so at least we can generate a negative voltage. Okay, this voltage is not very quiet. Now, one thing that we do have going for us is that this is a differential configuration. So at least the noise couples into both the top op amp and the bottom op amp, and hopefully a lot of that cancels out at the ADC. Unfortunately, it doesn't quite do that. And the reason is, as I mentioned, is that there's going to be protection resistors, and there's no guarantee that these protection resistors are going to match. So on the top, you might have 100K for a protection resistor. On the bottom, you're going to ground it, so there's no impedance. And so if you look at the graph on the bottom right, you can see a lot of noise that's coupling into the ADC input. Okay, so this is looking not great. So what can we do about this? Okay. So one nice thing about delta sigma, as I mentioned, is it is very good at rejecting a lot of low frequency signals. Okay. So we can, so that's nice. However, the charge pump can still alias into DC if, I have this equation here, A times the frequency of the charge pump, or A is some integer, equals B times the sampling frequency. So you're still going to have some problems. And some things you can do to make life better is, first you can make, these integers high, right? And that gives us two benefits. Okay, so the first benefit is that higher order harmonics tend to have a lot lower energy than the lower order harmonics, so that's good. The other thing is, if the delta sigma is not designed to be, 100 gigahertz, it's not going to be very responsive to higher order noise anyway. Okay, so two good things happen when you do that. And the second thing, and I'm just going to briefly talk about this, the second thing is you can slow down the charge pump, and there's a pretty easy way to do that. We have these MOS switches. Let's make the MOS switches small, and so you get a little bit more RC filtering on them. Okay, but going back to the trying to make sure the charge pump doesn't alias into the delta sigmas is what we do is we have a master clock, which is going pretty fast, well, for us anyway, 300 kilohertz. And then we divide it down by M on the right, and that clocks the delta sigma. Okay, and then you can also see it dividing down by some other number that's powering the charge pump, and that goes into the VSS. Okay, so for us, M is 20. So what do we do for N? Well, this is something that we programmed in firmware. So let's just try out different values and see what happens. And it ended up being pretty logical. So you can see this shows the expected noise as a function of the divider for the charge pump, and the red line shows what the baseline ADC noise is. Okay, so you can see for multiples of 5, that doesn't look very good, and it turns out that that's coherent with what the ADC is doing. But for most of the other values, the aliasing is you're not getting a whole lot of noise aliasing into the ADC. So most of these integers work, and I can't remember. I think we chose 19 for the final value, but they all kind of work very well. And we can see, despite how noisy that charge pump is, it's not really impacting our thermocouple measurements. So this just shows a couple thermocouples. If you're interested to see how it works with all the different ones, you could check out the data sheet for the 2983. But you can see here that the RMS noise is well below 0.1 degrees C, even below 0.05 degrees C for the type J thermocouple. For a type K thermocouple, the RMS noise it can creep up to about 0.1 degrees C when the thermocouple temperature is very low and the cold junction temperature is very high. That stretches the edge of the charge pump. But most of it is very well behaved. The error is also well below 0.05 degrees C. So even though we have this very nasty charge pump, we end up having a pretty noise-free measurement system. And just for completeness, this shows the errors for all the other thermocouples that are commonly used, and they tend to be bounded by about plus or minus 0.05 degrees C for all of them. Okay. All right, another piece of bookkeeping here. Now, again, in industrial uses, it's not very nice to the sensors, so a lot of times the thermocouples may open, and they want to find out if the thermocouple did that. So a very easy way to do that is you can send in a current source, and if you send in a current source, then if it's open, of course, you'll get a high voltage. You can detect that with your ADC and say, oops, there's a problem. Okay. This is a very common thing to do in industry, but the issue is, once again, we want the user to be able to put in protection resistors. And when you do that, that destroys the accuracy of the measurement. Now you have this huge IR drop where you have this current that's going across these 3.2K resistors, and that's going to mess up your measurement of the thermocouple voltage. Okay. And the way we solve that, and we're going to talk about this a little bit more, is that we have a 3-converter cycle. Okay. So we do 3 different conversions, and on the very first conversion, we just start off with a very quick pulse, and then we measure it. If it's open, we're going to see that there's a problem on the first conversion. If it's not open, this has plenty of time to decay. So this decay is very forgiving for reasonable protection resistors, and we give customers information so they can model it correctly. And the timing, as it turns out, can fit the simultaneous cold junction measurements we want to be able to do. Okay, so that's thermocouples. The next sensor we're trying to measure is an RTD. So for those of you who aren't familiar, RTD stands for resistance temperature detector, which doesn't say a lot. It just basically means, a resistor that changes its resistance when the temperature changes. But in practice, usually an RTD is a platinum resistor. These could be very accurate depending on how much you want to pay for one. The range could be minus 240 C to 850 degrees C. Unlike thermocouples, they don't require a cold junction, so that's nice. And you can see on the right how they work. If you buy what's called a PT100, for example, it's designed so it's exactly 100 ohms at 0 degrees C. And if you look, it's fairly linear. I mean, it's not completely linear. There's something called Callender-Van Dusen equations, which will tell you how to translate the resistance to a temperature. So that's basically how an RTD works. And this is how you measure an RTD, and it's pretty simple. We like ratios. So what we do is we take a sense resistor, RS, which is very well known, very well calibrated. We put a current through there. We measure the RTD, and then we just compare the voltage of the RTD compared to the voltage of the sense resistor, and then that tells us what the RTD resistance is. Okay, and since it's a ratiometric measurement, which is great, it doesn't depend on the current, at least to first order. So that's all good. Now the traditional way of doing this is, when you do an ADD converter is basically a ratiometric measurement. It's measuring the input voltage divided by the reference voltage. So people typically take advantage of that. And so if you look on the right, you can see this path where the sense resistor is fed into the reference, and then the RTD is fed into the input. Okay, but there's a lot of limitations to that. The first one is that if the RTD resistance is greater than the sense resistance, then the ADD is going to saturate. So that's not a good thing. The other thing is that a lot of really good features happen when you put something into the input of an ADC. You get 1 RF rejection, you get 60 hertz rejection, external noise. There's some good stuff when you put it into the input, but that does not happen when you feed it into the reference. The delta sigma doesn't doesn't filter the reference the way it filters the input. So because of that, we just had a little bit more straightforward architecture, which is that we had separate buffers going into separate ADCs for both the sense resistor and the input resistor. Okay, so that eliminates all the problems we were talking about before. All right, so to understand a little bit more about what we're trying to do, we're going to talk about just ways of measuring a resistor. Okay, and we can go from left to right. So the easiest way to measure a resistor is you just, is what's called the 2-wire on the left, and you just send in a current, you measure the voltage, which is fine. But unfortunately, if you have any parasitic resistance, then that's gonna, you're gonna be measuring that as well, and you won't know it. So this isn't necessarily that accurate. If you go on the right, you have a 4-wire measurement, and I'm sure everyone here knows that's the gold standard of measuring a resistor. So you put in a current from, for example, from lead 4 to lead 1. You measure the voltage from lead 2 to lead 3. Any parasitic resistance doesn't matter. So it's a great measurement. But the problem is in industry, these leads could be really long. They could be on the order of 100 meters, for example. And they can cost money. So customers want to save money. So even though, they know that the 4-wire measurement is the most accurate, they may not use it. Some of them may use 2-wire. And then in between there's this configuration called the 3-wire, which is, I'll talk about this in more detail. It's less wires, and they care enough to do this just to save 1 wire. And it's a very common measurement. Okay. So now we have this, but let's talk about the easiest one, the 4-wire. Okay. Super easy to do. What could possibly go wrong? And the answer is, there's thermocouples. So if you look on the left, I actually didn't put in all the thermocouples that are in here because it would have been, thermocouples would have filled this whole diagram. But basically, we have a platinum resistor on the left, which I'm showing in this, I don't know what color that is, teal, I don't know. Anyway, so that's connected to some other wire, which is a different color. That goes to the chip. The chip has another thermocouple junction where you're measuring it. And if you look through this, you can kind of see that most of the problems are going to end up showing up on the right as basically a thermocouple voltage as a function of temperature. Okay, so that's going to mess up your measurement. So how can you account for that? What we did was instead of having, if the user wants, instead of them grounding it themselves, we provided our own internal ground. And what that lets us do is that lets us put in a current reverser. Okay, so we do 2 different conversions. Okay, on the first conversion, the current goes from the very top, flows through the reference resistor, flows through the RTD, and goes to ground. On the second conversion, we flip it. We put the current going up this way, through the RTD, up through the reference resistor, and then to ground on that side. And if you subtract those 2 currents, then you end up with, if you subtract the voltages that you get from those 2 different measurements, then you can get the average value of the RTD voltage, and in doing so, any thermocouple voltage gets canceled out. Okay, so it's sort of like a chopped solution in a way. So we tested that, and so if you look on the right, what we basically did was we put in an actual thermocouple, a Type K thermocouple in the node where you're measuring the RTD. And without any current reversing, you can see the temperature just fluctuate the air fluctuate all over the place. And you can see it going up and down when the air conditioning is turning on and off, basically. And at night, the air conditioning stopped and, looks like it, kind of settled. But if you turn on the current reverser, then that air is basically gone. So this scheme works pretty well. Okay. So now that we've taken care of 4-wire, we can talk about 3-wire. So this, to show you how a 3-wire works, I'm just comparing it with the 2-wire. So with the 2-wire on the left, you send in a current, as I mentioned before. It goes through, the wire resistance, goes through what you're trying to measure, comes out, and you end up with an error term, which is, equal to the current times the voltage error is equal to the current times the wire resistance. Okay. The 3-wire works in a little bit different way. If you look on the right, you have 2 different currents, I1 and I2. You want them to be the same, but they may not be. And what you're trying to do is you're trying to measure the voltage across RM, the RTD resistance. Okay, you can't do that. You have to measure the voltage where the chip is, which is VM on this diagram. But if you look at this, you can see that there's going to be a drop on the top of I1 times RW1. Okay, on the bottom, you have a drop times I2 times RW2. And if you make I1 the same as I2, hopefully the wire resistances are the same, then that cancels out. And, at least theoretically, the voltage that you're measuring on the chip is going to be the same as the voltage that's actually across the RTD. Okay, so that's the idea. So there's 2 possible sources of error there. the first is the currents may not match, okay, but we can take care of that. And we do two separate conversions, and again, we sort of employ this chopping sequence. So on the first conversion, I1 is connected to the top one, I2 is connected to the bottom one. On the second conversion, the currents flip. And again, if you do some pretty easy math, then it's the same as if those two currents are equal. Okay, so now we've handled the idea that those two wires, the two currents are different. Now we have to deal with the fact that the wire resistances are different. Okay, so when you buy a 3-wire, they try to be at least somewhat careful that that those two wires are matched. So at least the matching is fairly good, and the wire resistance tends to be low. So the idea is that error term won't be too high, and you can reasonably, measure this RTD. Okay. So what could possibly go wrong? Yeah, we forgot about protection resistance. Okay. So now we're worrying about things that are on the order of 1 or 2 ohms and whether they're matched correctly, but all of a sudden we're going to stick in some protection resistors. Those can be on the order of 10K ohms. The user is not going to want to match these things, to within fractions of an ohm. They don't want to pay the amount of money. So it's very likely they might be getting 5% resistances. So if you do something like that, it's gonna destroy the accuracy of a 3-wire measurement. Okay. So how can we handle that? Well, we do have a lot of channels, and so we can actually exploit that. And the way we do this is sort of this hybrid 3-wire, 4-wire scheme. Okay, and what we do is we send in current through the bottom 2 channels. Okay, but we measure the voltage across the top 2 channels. Okay. Now we're going to have to add there's still a lot of protection resistors everywhere, but if you kind of study this a little bit, on the very top, you're measuring the voltage across protection resistors, but they're buffered, as we mentioned before, which means the input resistance is infinity and you don't get any IR drop across the top protection resistors. On the bottom, you definitely get, where I1 and I2 are, you definitely get an IR drop across the protection resistors, but you're not measuring anything. So if you do it this way, then all of a sudden the resistances for the protection resistors don't matter, and you're back to the accuracy of just measuring a 3-wire, just the accuracy of the wires that just go to the remote site. Okay, and as a bonus, this can also work for 2-wire measurements if you're trying to do input protection. So again, the 2-wire measurements may not be super accurate, but at least they can be a lot more accurate than they would be, without the scheme. Okay. So the next sensor we're going to talk about is a thermistor, and I love these acronyms because one's a resistance temperature detector. This is a thermally sensitive resistor, and it's the same. If you look at English, it's the same. But typically, thermistors are a very nonlinear material in terms of the resistance as a function of temperature, and you can see it has an extreme amount of change. The resistance as a function of temperature. So you can see on the left for cold temperatures, the resistance is very, very high. It's also very, very temperature sensitive. Okay, so that's actually a good thing in a way because any noise or errors or whatever gets drowned out by the thermal sensitivity of the resistor. So you can measure this thing fairly accurate, but the resistance drops down really quickly. From, for example, 500K to just 10K at 25C, and in that region, not only is the resistance smaller, but it's also less sensitive to temperature. So you need a little bit more sensitivity in your measurement. Okay. So there's a fair amount of challenges with measuring a thermistor, and I think we've addressed a lot of these. So we talked about the RSense voltage being below the ADC VREF. We're handling that with buffering. The fault detection, we've talked about the schemes with that. Ground reference input signals, we've handled that with the charge pump. We of course have to put in a lot of stuff into our processor so the user can get the right temperature. But the last one we have to deal with is that the resistance varies many orders of magnitude. Okay, so that should be a good thing, but it's not necessarily. Sorry, here we go. So let's imagine this for a second. we have to decide how much current we're going to send through this device. Okay, if we send in a large current and it's at a low temperature, then the voltage across this is going to be so high it's going to saturate the ADC. Okay, so okay, fine, you can lower the current, but if you lower the current, then if the thermistor is at a higher temperature, then all of a sudden the signal noise ratio is going to drop quite a bit, and you could introduce a lot of errors. Okay, but what we can take advantage of here is that, again, we're doing a lot of conversions just to measure one chip, or just to measure one temperature. So what we do is we divide this once again into 3 conversions. On the first conversion, we send in a small current. Then we get an idea of what the RTD's resistance, the thermistor's resistance is. Okay, and based on that, we have an algorithm which then adjusts the current to what's going to be the optimal value for measuring this. And that's going to be on the right. Then we do 2 different conversions where we can do our chopping and offset correction and all that other stuff. Okay. And the nice thing about this is, this sequence of 3 different conversions aligns with the sequence of the thermocouple conversions, and that means that we can still use a thermistor as a cold junction for the thermocouple. Okay, and this shows the result of that. So if you're looking at the thermistor errors, once again, is very low, within plus or minus 0.05 degrees C over the entire temperature range. Okay. Okay, and finally, this chip measures diodes. Now, the way you measure a diode basically is you stick in 2 different currents, okay? And if you stick in 2 different currents, you measure the VBE of one current, the VBE of the other current, and then there's an equation at the bottom where you can just look at the difference between the 2 voltages that you're generating, and then you use this formula at the bottom to get the temperature. And it's a pretty well-behaved formula, which is really nice. On the right, you can see it's on the denominator, you see it's proportional to the log of the 2 different currents, of the ratio. So once again, we like ratios a lot. Even if you don't know what the exact current is you're sending through, you could do a lot of dynamic element matching to make sure your ratios, the ratio is very well controlled. Then you have a K over Q. Those are physical constants, which is great. But on the left, there's this N. That N is the ideality factor of a diode. And as this crowd probably knows, it basically shows how many problems this diode has. If it's at 1, then the diode is an ideal diode, but it rises if the diode has some non-idealities. And one of the issues with that is that this ideality factor can change as a function of current. So I want to give a quick shout out. This is from my from my professor when I got a master's, Bart van Zeebroek, and he's got this online book called Principles of Semiconductor Devices, and it shows that the diode has different regions. So for very small voltages and very small currents, you can have depletion region recombination, which can degrade your ideality factor. And at the high currents, you can have things like, high injection, you can get series resistance, and then there's sort of a Goldilocks area in the middle where it acts a little bit more ideally, okay? So what you really want to do is you want to be able to, if you're going to send in 2 different currents and hope for the same ideality factor, you really want to be in the right region. And this one, we can't necessarily control what kind of diodes the customers are going to be using, but we do give them the ability to choose different currents so they can get into that ideality zone. So not too fancy here, but the one thing I will mention is that you can either send in 2 currents if you want, or you can send in 3 currents. And it turns out if you go through enough math, and if you send in 3 currents rather than 2, you can cancel out any series resistance that you have in the diode. So now all of a sudden you can actually measure remote diodes pretty accurately. Okay, so let's put all this stuff together. So this shows the accuracy of these different temperature sensors, And you can see they're all pretty well bounded, except for the diode, which is a little bit above 0.05 degrees C. The other ones are very well behaved within, plus or minus 0.05 degrees C. And that's over the full range of, the full specified range of all these different sensors. Okay, and this is just a quick thing which I thought was pretty cool. So Electronic Design News had this thing called the ACE Awards for the ultimate analog ICs back when this was made, and so we won that award. So I just want to give a little shout out to the people on the left. So Dave Bliss is on the left. He was our digital designer. To the right of me is Grant Shadow, who's our layout engineer, and to the right of him is Mike Mays, who is the overall lead of the project. Okay, thank you very much.